Nice to see you all. Thank you for coming out. Thank you for coming back. Really appreciate it. My name is Frank Long. I am a strategy and service development consultant for whatever that means for Cambridge Consultants. We are effectively the nerds of the Capgemini group. So we work in deep tech. Personally, I do a lot in AI, but not exclusively. I look after our cloud-based AI platform, running workloads as diverse as synthetic biology, defense and security stuff, quantum, and we do a wide range of different projects in many different domains. I'm also, in my part-time, helping Telenor start up one of the first sovereign AI factories in Europe. So helping Europe get up to speed. My background, it's down there. There's a lot of stuff. So I want to talk about AI factories. But first, before I get into that, I want to talk about some trends that are going on in AI and where we are. What we've got, what we saw with the release of ChatGPT is we discovered that when you throw a hell of a lot of data and a hell of a lot of compute at transformer models, which is what underlies LLMs, you end up with some form of emergent intelligence. And that has scaled really well. This pre-training scaling has helped build better models. We then moved on to post-training scaling, which is then making models more relevant to the job and having different types of models that get better as you go along. We're fine-tuning, etc. And we're now at test time scaling. And this is effectively when you've got a system that is thinking, that's using techniques like chain of thought, it's calling tools, and there's a wide range of different stuff that it's doing while you're also running it. The scaling that comes from test time scaling is massive. Now, to be fair, these are NVIDIA numbers. They say that you've got 100 times compute demand for reasoning models versus just running a simple LLM. I would believe that, considering how much time was spent with these models, and you're ending up waiting for multiple minutes for a response if you ask something particularly complex. But this is a trend that's going to continue. We are improving at an individual model level, but the trend is clear. We're over the line of the scaling law. So, looking at this, the world is investing in AI. The US is investing $500 billion in large AI factories. Europe is about 100 billion, a little bit more, including, for example, 6 what they call gigafactories. So these are factories where you've got over 100,000 GPU nodes. That's an enormous amount of power. It's enormous scale, and it helps build these foundational and reasoning models. So if you look at where we were last year, where NVIDIA are predicting we'll be next year, we're 10 times more GPU capacity in Europe in those 2 years. That is a phenomenal rise. And all of those organizations up there in the top left are building an AI factory of some description, right? And you can see Telenor are one of the ones I've been helping get up to speed. So what do we mean by an AI factory? Now, the simple explanation of this is you take data, water, and power and turn it into intelligence. I don't love that description. I think it's a bit vague. So to be a bit more specific, it's about getting massive racks of enormous GPU systems that contain huge amounts of power. So, for example, NVL 72, it's about $3 million per rack, and it's 120 kilowatts. That is a lot of power to have in such a small place. And you've got data centers full of these things, right? And 1.6 exaflops, and the bit you say quietly is at FP4. If any of you understand benchmarks, you kind of got there's a little bit of a caveat around that. But these are not just data centers. This is not your normal data center. This is a lot more than a normal data center. You need specialist equipment. You need specialist water cooling. You can't just run a normal data center with 120 kilowatts on a particular rack and just not change a huge amount. It will go on fire, right? Fairly certain of that. So it requires water cooling, software, a whole bunch of other stuff. So for example, with Telenor, they're taking the waste heat from the data center that they've built and using it to heat 8,000 homes. Kind of gives you the idea of the scale, right? So we can heat 8,000 homes from a single data center. These AI factories need a whole bunch of software, going from controlling the GPUs and all the back-end networks, etc., all the way up to how do I build AI systems and models and all that good stuff. There's some of the software in the middle, around about here, that's relatively common with normal data centers, but everything else is fairly different and fairly specialist. So while it's a particular instance of a type of data center. Why do we need these things? Well, the best information I could find online was actually GPT-4 Turbo, which is 1.8 trillion parameters. That's actually relatively old by this stage. There are a lot bigger, a lot better models out there. These models are getting enormous. You cannot run these things on a normal graphics processor. If you've got a GPU from 2-3 years ago, you're not going to run a multi-trillion parameter model on it at anything vaguely close to a decent level of performance. So in order to be able to run all of these, you need this sort of level of kit, which is why governments around the world and organizations are spending a fortune on it. So that's the core. This is the massive power, lots of intelligence. This is what's the main driving engine behind the AI movement at the moment, the sort of stuff that OpenAI is big into. But that's not the end of the story. There's also on the edge, this is either on the network edge or on premises. So for example, in Cambridge Consultants, we have this box in the corner, which has a bunch of medium power GPUs. We call it Lamatron, and anybody can use that, you know, with a straightforward API call to call a bunch of models that we host on there. This is a very common pattern. And what we see is going to be a lot more edge deployments with GPUs on them. And I'll come back to that point later on. And then on device. So we're seeing things like NPUs. We're seeing things like the TPUs on the Pixel devices from Google. They're actually doing AI processing on device, and it's getting pretty good, but they're fundamentally limited. They've got really low latency because they're on your device, but they've got naff all power. They've got very little power. You're not talking 120 kilowatts, right, in order to power these things. So the amount of stuff they can do is fairly limited. And it's not just phones. It's cars, it's sensors, it's stuff that's located in the physical world. Right. Oh, there we go. Now, we're talking about hierarchy of intelligence. The human body does take a hierarchical approach to intelligence. We've got our brain, right? It uses an enormous amount of power. It is 2% of the weight of the human body, but it is 20% of the energy expenditure, right? That's a lot, but that's because it's doing a lot. It's doing your reasoning, it's centralized, it's making decisions. The rest of your body, the nervous system, has a certain level of innate intelligence with your autonomic nervous system, but it handles things like sensing, your touch, your ability to feel, and perform actions and operations. Some of it is under direct control of your brain. Some of it, your heartbeat, things like that, are not. And it depends on what's happening, whether or not you are controlling it. So for most scenarios, you are not controlling your breath, but you can of course control your breath. So I think this is a really handy analogy to think about what use you're going to put to your AI when you're putting AI systems into production. So this analogy holds with regards to the AI systems. Reasoning, they use enormous amounts of power. They're very powerful. They need specialist equipment. They need a brain that uses a huge amount of power relatively. But with the body, there are lots of different types of AI. And here's a very small subset. So Gurpreet already talked about small language models. GenMet 3, for example, operates on Google devices. One that we're very keen on in Cambridge Consultants, and one that I spend quite a bit of time on, is multi-agent reinforcement learning. And this is, for example, something that we built for the UK's Defence Science and Technology Laboratory, where you can use these tiny agents to defend against attacks, defend autonomous vehicles against cyber attacks. So it can detect whether or not it's a DDoS attack or false alarms or data injection, and then take actions in order that the vehicles complete their mission. These ones, they run on Raspberry Pis. We can run 8 of them on a single Raspberry Pi. Right? So that's a different order. That's a very different type of AI. And then there's the physical stuff. Robotics, you're going to see an enormous amount about robotics. But one of the keys with this is you need digital twins in order to build them. And the type of AI you're using there is not going to be the generative AI that everybody's talking about, right? It's just not going to work when you've got a battery and you're trying to do a hell of a lot of other things as well, besides from being intelligent. Okay? So we've established that on device, you've got limited power. So it means that if you're going to do cognition around that device, you probably need to move that cognition somewhere else. And where else are you going to move it? Well, you can move it to the edge. You can move it to those edge locations. And you're seeing a lot of this in industry, where companies will have small set of servers that they're or GPU servers that they're using to serve the local industrial space, usually over a private network. But you've got the core where this is in hyperscalers, the likes of Google's, the likes of AWS, and Microsoft. Jeepers, I almost forgot about Microsoft. That would have been a mistake. But the thing about this core is, when you talk about hyperscalers, 95% plus of the hyperscalers are American. They are Oracle, they are IBM, Google, Microsoft, AWS. And that has some geopolitical risk, especially when it comes to things like defense and security. And if you have a situation where you are concerned that there is a chance your organization, your government, if you're Danish, this is super important, might be sanctioned and might have your systems turned off. And I'm afraid you're probably going to have to build yourself an AI factory. So this is a really interesting mix between IT and geopolitics that's going on today. Now, telco networks are all over this. This is super important for telco networks. So the vast majority of telco networks, over 65%, are aiming at having fully autonomous operations by the end of 2030. This is TM Forum, or the organization you look after this, level 4 for any telco nerds out there. But in order to do that, you need to be able to run your operations in a fully autonomous fashion. You need your system to be able to understand problems, detect them, and remediate them. It also has to then help your physical teams to actually understand what the hell is going on, because now you've got AI everywhere. They're proposing solutions. So today, it's just being used to review the status of networks, flag issues, propose solutions. Funnily enough, this exact hierarchy working with a water company. They do exactly the same thing because it's a utility. But then they've built these large telecom models, which have taken in all of the log data, all of the previous actions, details of outages and incidents and remediation, etc., and then built a model of how the network works. So instead of human language, it's using telecoms information as the basis for a foundation model. And so, for example, SoftBank can now create the configuration for a base station. Used to take 2 to 3 weeks. They can now do it in about 10 minutes. And they're getting 95% plus accuracy on creating that configuration. Massive time saver. It's also a starting point for automation because you can then deploy things much more autonomously and much faster, and you can provision and deprovision, so you can take it on the network and take it off. And then at the lower levels, managing day-to-day, operating, making sure that what you're actually serving from a telecoms point of view is good. So for example, one of the things we're doing is taking those multi-agent reinforcement learnings and using them to control the radio access network. So for example, we've created a model of Paddington Station, and trains come in and people filter through, so you need to ramp up the capacity, you need to ramp up the usage. And then, you know, it's a bit quiet, there's not very many people around, turn the entire thing down, just turn it off. And you've got agents as well that can then detect what's the experience of individuals within the station. How could we possibly reorientate the network to improve their experience? You know, there's this dude over here who's consuming a huge amount of bandwidth. It's not a problem, give him a bit more bandwidth. Okay, let's do that. So this is the sort of operation at a physical level that we see actually going into practice. So we're working with networks in order to build this out as a thing into the test network. So that's the level of maturity it's at the moment. So there are challenges, and I realize where I am, so the security stuff, go. So there's other people to talk to about that, but security is a challenge, right? If you've got agents doing stuff across different types of AI, you've got different levels, it gets very complicated very quickly. Really, really complex. How do you know what agents are allowed to do what? And having a static kind of role-based approach is definitely a bad idea. You know, there's different approaches, and I'm not going to go into which ones I would recommend because I'm not the right person to do that. There are people out there that are. With regards to the data consistency and the model synchronization, say you decide you're updating your big brain model that is reasoning and doing all your planning. Have you updated your models below that are actually implementing that on the ground, or are you losing synchronization between those models? Because if you're not testing that end-to-end, and coming back to Gurpreet's point, you know, CI/CD, fantastic for that, you know, you're going to lose synchronization, and this, you're going to lose functionality. It's the same thing with the training data. If different models see different training data, you risk having a problem where their view of the world is not the same as a view of the brain. And I think it's fairly clear that we're talking about, there's a big coordination challenge here. MCP is one possible solution. There's a wide range of different inter-agent communications, but it's not just between agents. This is between different types of AI. Some of them may be agents, some of them may be more traditional AI, right? How do we make sure that we've got that communication working? Some of it might be digital twins, as per the robot example. Trying to make all of this sync up, make all of this work, is a major challenge. I don't think we're anywhere close to solving that whole story yet. Explainable AI is one place to start. I mean, to use Gurpreet's terms, observability, right? Start with observability and start with how do you understand it. And you know, it comes back as well to Sonia's point on how do we make sure that we understand what we're putting into production. So being able to observe it is the starting point for control. Right. So in conclusion, there's lots of different types of AI. Big AI, small AI, physical AI, etc. There's a lot of challenges here, but we can now start shifting into the physical space. And with agentic AI, it really unlocks a whole bunch of really exciting opportunities when it comes to autonomous systems and making systems truly autonomous. But there is a lot of work to do, and in order to do this efficiently, cost effectively, you need to think of which compute is the right thing for your particular use case, and how do you balance all of those considerations. Thank you very much. Any questions?